Hello, my name is Jared Skeens and welcome to the Zoom room. Today we're going to cover Pure Math 1 Functions, Part 4, Domain and Range. So finally here we get to the domain and range as we've kind of talked about it little bit by little bit. I keep kind of pushing it off so that you can focus on some of the other skill sets. Now that you've went over composite functions, inverse functions, and a little bit of graphing, now I think that we can kind of tie it all together a little bit and really focus just on domain and range. So there are going to be 4 applications that we look at. We're going to look at the application of the domain and range to just an individual function. We're going to look at specifically domain with a one-to-one function, and we'll define that for you later. And we'll look at it with composite functions. This one is kind of tricky. Takes a little bit of thinking on how that works. And then we also want to look at it with respect to inverse functions, which we saw a little bit of that back in part 3 when we were looking at graphing the function with the inverse function. So one of the things that we're going to see is that usually there is provided for you a domain statement. Now, why the domain statement? Why do they give you a domain statement and not always the range? Okay, well, because X is the independent variable. If you remember back in IGCSE, sometimes when you wanted to graph something, you would make a little XY chart. And you would pick numbers for X, plug it in, solve for Y. X is your independent variable. That's the one that you select numbers for. Y is the dependent variable. It depends on what all this here calculates up to. Okay, so because X is the independent variable, then usually the domain statement is the main statement. Range is kind of optional, and range, because it is from a dependent variable, is a little bit more difficult sometimes to figure out. Sometimes you have to be a little bit more graph savvy to figure out range. Okay, so let's work through these. So the domain statement is going to basically reflect one of 3 thoughts. The domain statement will either tell us invalid values, in other words, values that you cannot use, or a domain statement will tell you valid values, that is, the values that you're allowed to use, or sometimes a domain statement will limit the values. Even though maybe you could have more values that you could use, maybe they only want a section of the graph, so they'll limit the domain. So you need to be able to work and understand these statements, okay? So 4 applications, 3 ways of making the statements. So let's start with our first one just by looking at an individual function. Now, normally they're not going to ask questions specifically for an individual function. Usually that will be provided. But this is the foundation for your understanding how one function then interacts with another function, especially when we get to composite and inverse functions. Okay, so let's start with the basics so that you can hopefully understand this concept of domain and range. First off, just in case you haven't figured it out, the domain is actually your X values, the values along your X-axis that you're allowed to use. The range is the Y values on the Y-axis, okay? So when we talk about domain, we're talking about X-axis values. Range is talking about Y-axis values. The words actually kind of mean the same thing. You have a king and his domain. Well, his domain is the area over which the king rules. You have cows out on the range. The range is the area the cows eat their grass. So both of them refer to an area. So they kind of have similar meaning, but they choose the different words. One is always for X, that's domain. The other one is always for Y, that's range, okay? So now that we got that straightened out, we're going to look first at our domain statements. So what a domain statement looks for is there any value that cannot be used? Well, when you have a fraction, you're not allowed to divide by 0. I'm not going to get into that discussion on why you can't divide by 0, but if you try it in your calculator, you're going to see if you divide by 0, you get syntax error, okay? So we're not allowed to do that. So if we can't divide by 0, then that means this 3x minus 2 cannot be 0 because we can't divide by a 0. Now x could be 0 because then you would end up with a negative 2. So sometimes your x can be 0, but you got to make sure that this denominator does not become a 0. So we take the denominator, say it cannot be 0. You solve it like an equation. And so you say 3x then cannot be 2. X therefore cannot be 2/3. This then can be one way of stating the domain, is stating what x is not allowed to be. Now, if you have a linear function like, for example, y equals 2x plus 5, there's no fraction in it. There's no radical in it. So if there's no invalid values and you don't have any particular reason to limit the values, and if x can be anything, any value at all, then you would say x is the element from the reals. The only thing that we're limiting is not complex numbers, that is numbers that involve imaginaries, which gets us to this. So x can be all reals, meaning any number on your number line can be plugged into the equation. So this would be your generic domain statement with anything. But if there is something that is not allowed, then that is one way of writing a domain statement, is an valid or an invalid value, okay? So you should be able to look at a fraction and determine what x cannot be if you have a fraction, okay? Now, if you have a radical, you're not allowed to have negatives in the radical. Again, you can try it on your calculator. If you try to take the square root of a negative number, you're going to get syntax error again. And that's because square roots of negatives take us into imaginary numbers, which is a part of the complex number set. So it's outside the real number domain. And so when we're working with real numbers, we cannot allow imaginary numbers. So that means that what is inside the radical has to be greater than or equal to 0. In other words, it can be positive, it can be 0. You can take the square root of 0, but it cannot be negative. So when you solve this, you get x greater than or equal to 5. Okay, and that would be the domain. This one would be valid values. That's an example of number 2. So example of number 1 here was finding an invalid value, one we cannot use. Example number 2 is finding the valid values. It's a set of values that we can use. And so obviously we can't use anything that would cause a negative here, but they state it in the positive way instead of stating it in the negative way. Usually if there's only one value you can't use, it'll be stated in the negative way. If there's a set of values that you can use, or if there's a set of values you can't use, they'll state it towards the positive way. That means towards the values you can use, okay? So that covers fractions, and radicals are really the only two things that you have to worry about concerning invalid numbers. But then there's a third way that statements are made, and that is maybe you don't want the entire graph or the entire solution set. Maybe you want to focus on just a part of the graph or a limited part of the solution set. So if you look at this equation here, this is a reciprocal function that normally is at the origin. It's been shifted to the right 2 and up 3. I don't know if you remember your parent functions from IGCSE material. A lot of students forget this graph type. Makes a graph in this kind of shape. It's been shifted 2 units to the right, 3 units up. And so this is the graph that you get. If you forget the graphing, it's not super important, although the more graph types that you become familiar with, the better you'll have success at finding domain and range, especially range. Range is often more visual toward the graph, whereas domain, you can kind of figure it out a little bit more algebraically. So anyway, we get this divided graph, part of it over here, part of it over there. Notice it still does pass the function, the vertical line test. It is a function, but it has 2 parts to it. So what sometimes math curriculum will want to do is it will only want to deal with maybe this one over here. So this one here is 2, and it keeps going that way. So it might make something like just x greater than 2. Notice it can't put equal to because you can't divide by 0. That goes back up to here. So instead of just saying x cannot equal 2, which it could, it's not just trying to show something invalid, it's wanting to limit the set of values that you're working with. It doesn't want to work with this side over here. So it can say x greater than 2. If you're greater than 2, then obviously you don't have to worry about the invalid number, okay? Or it might say something like x greater than 2, but less than maybe 10. So in other words, maybe instead of having it go completely forever, in that direction, maybe they want it to stop out here somewhere. So it can get close to 2 without actually reaching it, and all the way out to and including the 10, okay? So again, there's basically 3 ways of writing a domain. Writing it for what number does not work or cannot be used for some mathematical reason, usually divide by 0, can't, or stating the valid values, such as to avoid getting a negative in the radical, which also we don't want at this point, or because we don't want the entire graph and we only want part of the graph. So we can select which part of the graph that we want to deal with. These are the 3 main purposes for a domain statement. And so when you see like this, or like this, or like this, it then helps you to understand that you're dealing with only a part of the graph set itself, okay? So this is fundamental to these other applications, okay? So I'm going to set up for the second one here, one-to-one function. Okay, now we're moved on to the second application, one-to-one function. Now, maybe before I get started on this, you might ask, we just covered domain on functions. Why didn't we cover range? Domain is what is usually provided. So I didn't cover range for the basic function. That's something that we can look at later. Normally, that's not provided at the beginning, and it's something that is sometimes asked. So we will look at range in some of these examples, like we will on this one, but for a normal function, usually it's the domain statement that you focus on. Now we're getting into one-to-one function. First off, you say, what is a one-to-one function and what does it have to do with our question types? A one-to-one function is a function that passes both the vertical line test, which is what classifies as a function. So a parabola here passes the vertical line test. That is, if you were to draw an imaginary vertical line, it only touches your graph at one point. However, if you take and do a vertical line test, a horizontal line test, it passes the vertical line test and therefore is classified as a function. But it has to also, in order to be a one-to-one function, has to pass the horizontal line test. So here's my horizontal line, and as you can see, my horizontal line, it touches in more than one place. So right now, this parabola does classify as a function, but it does not classify as a one-to-one function. Now, what is the significance of this? Well, if we want to find the inverse of our parabola, which right now is a function, it does classify as a function, it passes the vertical line test, so it can be written as f of x. But if we were to draw the inverse, meaning it gets reflected over this and you change your x and y values switch, remember we talked about that, the inverse would look like this. Okay, see the reflection there? And this would go like this, and you see the reflection here. Now, you get a graph, yes, but it fails the vertical line test. If you draw a vertical line, it's touching at two places. It fails the vertical line test, which means this is not a function and it cannot be classified as an inverse function. So that creates a problem. Our original is a function, but when we follow that function to inverse, we now fail to end up with a function for the inverse. So what we need to do is we need to break our original graph into right half or left half. Okay, so we're going to look at the vertex here. That's going to be key, is looking at the vertex, and we can either take the right half of the graph, in which case x would be greater than or equal to a particular value, or we could take the left half of the graph, in which case x would be less than or equal to a particular value. We're going to start with the right-hand side. If instead of taking the whole function, yes, it is a function, but it does not create an inverse function. So we get rid of that left-hand side and just work with the right-hand side. Now, when we go to do the inverse, we get this. And this does satisfy the vertical line test. So where this one can be our function, then this one, so this is our f of x, then this one here is our inverse function, meaning it still classifies as a function. Whereas over here, yeah, we had a function to start with, but this actually cannot be classified as a function. It is a graph. It is x equals y squared, but we end up getting two values for y. So we cannot classify it as a function. In other words, this graph does not have an inverse function. Okay, so that's the problem that we run into with quadratics, is we cannot use the entire graph to create an inverse function. Okay, so what we need to do is we need to limit the values, and the most obvious place to make that limit is from the vertex. The vertex is going to be the point where the curve wants to come back on itself. So that's the halfway point. So you could break it somewhere else as long as the graph doesn't come back on itself. But the most obvious place would be the vertex. So if you break off the left and keep the right, you're going to have x greater than a particular value, and that value is going to be the x-coordinate of your vertex. Okay? Now, if you took the left-hand side, which would be x less than a particular value, and you found the inverse would look something like this. You can see it folds. Again, passes the vertical line test. No problem there. Probably should have made it a little bit more curved like that. Passes the vertical line test. So this is our original part of the function, but limited the values to only half of it. And then this one would indeed classify as an inverse function. So the issue is being able to have the inverse still classify as a function, still pass the vertical line test. That's the issue. So when we say one-to-one function, it means that your original graph passes the vertical line test, meaning it's a function, but it also needs to pass the horizontal line test, which a full parabola does not do. But a half parabola passes the vertical line test, it's still a function, and it also passes the horizontal line test. So that is what makes it a one-to-one function. So in Cambridge questions, it's going to say one of two things. It's either going to say one-to-one function, so you know right away you need to limit the domain, or it's going to say so that it has an inverse. Something about having an inverse function, okay? So having an inverse function, or being able to have an inverse function, and one-to-one are just two ways of saying the same thing. You need to limit the domain, and you're going to do so by selecting one way or another from the vertex. They will give you a statement like this, meaning you have to come up with the number, okay? So if we look at this up here, okay, we look at this up here. Let me get rid of these for right now. Okay. Look up here. Here would be a standard form of a quadratic. Normally, they're going to start you there. I'm not going to start us there because to get from there to here, you have to do completing the square. We already did completing the square back in the quadratic section, and I don't want to take the time to complete the square. So I'm starting us off in the complete the square. So most likely, if they ask you for a domain statement to make it a one-to-one function, or saying what should the domain be, what is the value of k so that our function can have an inverse. If they say something like that, most likely that is going to be either already in complete the square form, or it's going to be in standard form, and before you get to that question, you're going to have to complete the square in one of the previous parts. So again, look for those linked concepts within the different steps of your question. So if they don't tell you to do that, you're going to want to complete the square anyway, because you need to identify the vertex. So if you remember, this is vertex form. The method is completing the square, and you identify the vertex, remember again, is opposite of the x, the same as the y part, or I called it h and k when I did the video on that before. Okay, so our vertex you should recognize as 3, 5. Now this is a domain statement. Remember, domain deals with the x value. Okay? The question is, which half do they want? Do they want the right half, or do they want the left half? And again, that will already be provided as a x greater than or equal to k or p or some variable that they give to you here. And what's going to be important is that you also look at something like, if it's like this, they're going to say, what is the least possible value of k? Or what is the greatest possible value of k? Let's look at that for a second. If you are, here's our parabola. I'm not going to put it specifically on a graph. So here's our vertex. Our vertex is at 3, 5. So this is our, on the y-axis, this is our 3 here. Okay, I'm sorry, on the x-axis, this is our 3. So if we want greater than this value, that means all these values over here are good. Good, good. So if you're coming back to it, you can have 10, you can have 5, but the least or the smallest, they can use different words, the smallest or least value that k can be is the 3. That means all the other values have to be bigger than that. So what your domain statement is going to be, your domain statement is going to be x greater than or equal to 3, but your answer to the question is specifically about the k. So you're going to say k equals 3. That is the least value that k can have. So the way they word it is quite interesting, and sometimes students don't know what to do with it. So they're really looking for one number, the smallest number out of the possible numbers. So your domain statement is actually x greater than or equal to 3, but what they're specifically looking for is this least or smallest value of k. So k equals 3 is actually what they're looking for the answer. Okay. Now, same way as if they go x less than k, meaning they want the left-hand side of the graph. They don't want that side. They want the left-hand side. So they want less than or equal to 3. That means you could have -10, you could have 0, but the greatest value that you can have, the greatest means the furthest this way that you can have, is the 3. So again, the domain statement would be written like this, x less than or equal to 3, but of those values, the greatest value for k is going to be 3. So again, you would put k equals 3. So that helps you hopefully understand how to write your answer, how to write the domain statement, and what this one-to-one function means you got to cut your graph in half so that when we do that reflection over the axis of symmetry, we still have a graph that classifies as a function. Now, there's one other area where this is important. when you take a quadratic and you find the inverse function, maybe I'll wait until we get down to the inverse, since that's going to get into the inverse. I'll wait to that for 4. But this is going to be important. Let's go back to range now. So that's how you find the domain, where the domain normally could be all real. We want one-to-one function, means we got to cut it off at the vertex, either go greater than or less than, depending on what they want. Now, for the range, well, the range has to deal with the y value, okay? Your range deals with the y value. So if, again, you had your graph here, and this is your vertex 3, 5, then that means your y-axis starts, your y values start right here with the 5, and they keep going up. So your range would be y greater than or equal to 5. Or you could write it in function notation, where your f of x is greater than or equal to 5. Okay? So the range, once you've established your vertex, it gives you both a value for one-to-one function, and it also gives you your value that you need for your range statement. Now, if your graph faced downward, let's say this is the point 3, -2, remember your graph will face downward if you have a negative on your x squared, your parabola goes down. So if you happen to have a downward facing parabola, meaning you have a negative here, or you would have a negative out here on this, if it was in the complete the square form, then your range would be, your function of x would be less than or equal to -2, meaning it starts at -2 and your y values go below the -2. So remember, range has to do with y values, domain has to deal with x values. So here's the domain and range dealing with a quadratic, especially when you want to create a one-to-one function. So Cambridge will only use this one-to-one function with quadratics, meaning at some point you'll have had to complete the square. When you interpret the complete the square, it gives you the vertex. The vertex automatically is what helps you figure out domain and range. If you notice the point values on those domain and range questions, assuming you've already done the complete the square as a step before that, they'll only be worth 1 point. You don't really do any math. It's pure recognition as to the meaning of those values. And that then becomes your domain statement or your range statement. So you got to understand the meaning of those values with respect to the graph and domain and range. Okay, so let me set up for the next example. Okay, now we're moving on to number 3, composite functions. Composite functions are the ones that get a little tricky because you're dealing with multiple functions at the same time. So here we have an f of x function, 48 over x minus 1, and the domain is provided for us. But then we get to the g of x function, 2x minus 4, and the domain is not provided for us. So the question says, find the greatest value of a and the least value of b that allows for this composite function. So the key to this is paying attention to the way that this composite function is arranged. So remember that your f function, here your x goes into the f, and then your f of x is what goes into the g. So our f function is being put into the g. And the f function, we have been given the domain, and it is limited, meaning that the values then that move on into the g are also limited. So that's what we want to work with, is taking the values that are allowed to put into the f function, finding what those values are, that will then become the domain of the values that are allowed into the G. So again, you're still working from the inside out. So x can only be from 3 to 7. So if we put f of 3 down here, we get 48 divided by 3 minus 1, 48 over 2, which is 24. If we take f of 7, then that means we're going to get 48 over 7 minus 1, which is 48 over 6, and that comes out to 8. 6 times 8 is 48. So here are our two values that our f of x is limited to what can go into it. So when we put that into it, the output of our f of x function will be between 8 and 24. It's our f function output that is then put into the G. Okay, so the input into the f function is the x. The f of x is then the output, and that then becomes the input into the G of x. Now, the trick is looking at these. Okay, the trick is looking at these words, least and greatest. So you might think, well, the least is 8 and the greatest is 24. That's not what it means. What it means is the greatest value of A. A is on the left-hand side of our domain, meaning as we look at the number line, it's going to come up to a particular value that A can be. So because we're going this way along the number line, A is going to be the biggest of those values on the left-hand side. It's on the left-hand side of the domain. So on the left-hand side of your number line, as you get closer to a point, it's going to come to a point that finally A is allowed. So what is that greatest value that A can be? So that greatest value is the 8. So this is going to be 8. And then here, it's the least value of B. B is on the right-hand side of the domain. So the right-hand side of your number line is over here. So you're going to come down to a particular value. So we're actually going this way on the number line. What is the smallest value that B is able to take? It's the values in between that make up the domain. So our domain is between 8 and 24. 8 is the largest value coming from this side of the number line. 24, that's the greatest value for A. 24 is the smallest value that B can take. So the actual domain is between 8 and the 24. It's between the 8 and the B. So that can be a little confusing. Understanding the greatest and least with these two numbers has to do with the perspective of which direction you're coming from on the number line. Okay, so keep that in mind, and I'll set up for another composite function just so that you can see how it works when you're working with multiple functions. Okay, here we have another example where they give us f of x equals 2x plus 3. The domain is given x greater than or equal to 0. They give us a g of x function, but they don't give us the values of the g of x function. They just say it's ax squared plus b, so we don't have the coefficient or the b term, and they don't give us the domain x less than or equal to some number. They do give us the composite function in this case. So the composite function is 6x squared minus 21. So what we need to do is we need to find the values of a and b, and we need to find the greatest value of q. This is the first half of the question. So what you need to do, again remember is how a composite function is put together. It's your x goes into g and your g goes into f. So if our g, we don't know the x to put in, but whatever this value is, our g of x is going to go into f. So our f of g of x is going to be 2 times ax squared plus b plus 3. Okay, so g of x is put into the x of the f of x. Okay, so all of this goes into the x there. So 2, here's our x, the g function is plugged in, then plus 3. So if we simplify this out, we get 2ax squared plus 2b plus 3. Well, if we compare that to this, and we do what's called equating coefficients, meaning this is our x squared term, here's our x squared term, that means 2a has to equal the 6. So a equals 3. So that's one of our answers here. Then the 2b plus 3 is the negative 21. So 2b plus 3 equals negative 21. Subtract 3, 2b equals negative 24. Divide by 2, b equals negative 12. So we got the a and the b. Now we got to figure out this q part, okay? So here we have, we can rewrite this, get rid of this really quick. So this is 3, and this is actually a minus 12, and that's our g function. Now we want to look at this and come up with our q. Okay, so to come up with our q value, we need again to remember the order in which our composite function is. We came up with our a and b from the g. The g is put into the f. Well, the f has a limitation on it. So we can't just put any g into the f. We can only put g's into the f that satisfy the allowance to get into the f. This tells us what can go into f. And since we're putting g into f, then that means our 3x squared minus 12, whatever that value is, in order to put it into f, it has to satisfy the rules of getting into f. So G is going over to his friend's house, G is going over to his friend F's house, so he has to follow the rules that are at F's house, which is this. So greater than or equal to 0, 3x squared is greater than or equal to 12, x squared is greater than or equal to 4. Now, remember when you square root, it gives you the plus or minus. So when you square root, the positive one will be x greater than or equal to 2. The negative one is going to be x less than or equal to negative 2. Remember that plus and minus? The plus does not affect the inequality. The minus flips the inequality. Radicals are a fast way of dividing, and when you divide by a negative, it flips the inequality. So that minus sign flips the inequality, and you get less than or equal to negative 2. How do you know which one to choose? Well, just look at the format. The format says less than or equal to. So the one that says less than or equal to is this one right there. So our Q is a negative 2. What is the greatest value of Q? The mean. Now, greatest value doesn't mean you pick the bigger between 2 and negative 2. Remember, you follow the inequality. So x has to be less than that. So in other words, everything's over here on this side of the negative 2, meaning because it's x are the values less than the -2, that means -2 is the greatest of the values of that set. If it were facing the other way, like the greater than or equal to, then 2 would be the smallest value of this set because it would go from 2 and it would be going that way. See, this is x less than -2. -2 is the greatest for this set. This one, 2 is the least of that set if x is going greater than the 2. Okay, so be careful with those. It's a matter of perspective of where you're at on the number line. It does not have to do with the greatest of the values that you get in your solving. Okay, that's where it's confusing. So it has to do with the perspective of the number line. So Q is -2, A was 3, B was -12. Let me set up so that we can see the second half of this question. Okay, the second half of our problem, we got -2 as our answer for Q in the first half. Now it goes to a different situation. It says now your Q is a -3. So I erased the -2, now have put in the -3 because it's a new half of the question. So that -2 isn't relevant to this half. And find the range of f of g. Find the inverse function of f of g, which we're not going to do. We're not going to do this because we already covered how to do the inverse. But we will look at the domain of f of g, of the inverse, and we can do that even without actually finding the inverse first. Okay, so first, the range of f of g of x here. So our f of g is this. Now, if you put this into the complete the square form, this is actually like a 6x minus 0 squared minus 21. In other words, it's already in the complete the square form. You might not have recognized it. There is no number attached to the x, meaning it's like a 0. So the vertex of this is really 0, -21. Okay, so the vertex of r is at the x equals 0, but our x can't start until -3. So if this is our 0, -3 is over here, meaning, and it's less than. So really, we're only dealing with this part of the graph. Okay, so 0, -21 is the vertex, but our domain actually doesn't even include the vertex. It has been, that part of the graph has been eliminated from our accepted values. So we're only dealing with this. So if we want to find the range of this, all we need to do is plug in our x value, -3, and figure out what the y value is, you know, on our axis here. So this is all the way down at like -21 here, or the vertex was all the way, you know, down here at -21. But we want to find out where that y value is at -3. So we can't use the -21 for our range because this got cut off from our domain. I hope you understand that this graph went like that. Normally the range goes from the vertex, but because this part of the graph got eliminated, we have to figure out our range without looking at the vertex. So plug in our -3, so we get 6 times -3 squared minus 21, 6 times 9 minus 21, 54 minus 21 is 33. So our range is going to be, our fg of x will be greater than or equal to 33. Okay, so that is the range for this particular function. Now, says find the inverse function. Like I said, we did inverse function in part 3. So I'm not going to do that for you. You can do that since you've already learned it. But it says find the domain of the inverse. Remember, for inverse function, and now we're kind of moving down to our 4th application here. Now we're on inverse function. See how they blend together? They just went from composite function now to the inverse of a composite function. So we just switched applications all of a sudden. We're now on inverse. And remember that your domain of a regular function becomes the range of the inverse, and your range of the original function becomes your domain of the inverse. So actually, you already found it. This is the range of the regular function, meaning our domain of our inverse function is x greater than or equal to 33. It's right there because range of regular function becomes domain of inverse function. See, those are the things that you're looking for, is understanding how it works. There's no math to it. Sometimes there's a little bit of math, but sometimes it's just a matter of interpretation. That's why it's important that you understand how these domain range statements work. I think I have one more example for us. Okay, here's our last example, and actually I've simplified it for us. Remember when we have our quadratic function, which usually it's bigger than this, I've just simplified it to x squared. You have the parabola. We looked at the one-to-one function back up here, where we have to either choose the right hand or the left hand side. So we dealt with that back to one-to-one function. But what we didn't get to is how does that affect the inverse function? Now that we've moved down to our application to inverse function, we need to revisit that one-to-one. So notice on a normal parabola, your domain could be all reals. Okay? There's no invalid values, and we don't necessarily have to limit it unless it's a one-to-one function, meaning we want to create the inverse function. Okay, so since we want to have the inverse function, then our original function has to satisfy the one-to-one. So what happens is you're going to either select the right-hand side or you're going to select the left-hand side, depending on how the problem sets up the domain for you. They'll set up the x greater than or equal to k, or x less than or equal to k, or some other variable. And you need to, again, do the complete the square, and you select it based on the x coordinate of the vertex. So I'm skipping the completing the square and just simplifying our quadratic down so that we don't have to focus on any of those other things. So the basic quadratic is x squared. So you either have the right-hand side or you have the left. Well, that's going to impact the inverse, because if you choose the right-hand side, then your inverse is going to look like this. If you choose the left-hand side, the less than 0, your inverse is going to look like this. So what happens is this. When you go through that inverse function method and you switch your x and y and you solve for y, notice you get a plus or minus root x. Well, the plus root x is the top one, and the minus root x is actually the bottom one, but we can't have them both together because it fails the vertical line test. And that is why we had to choose one side or the other. We couldn't have the full parabola together because we don't want that full inverse fails the function test. So it can't actually be called an inverse function. So this also has the vertex. This is the positive root x side. This is the negative root x side. So notice if you're going x greater than 0, then that means you're going in the positive direction. So if this is your f of x and this is your inverse of x, and you're going greater than 0, that means you're going in the positive direction. So you're going to take the positive root. Now remember, your quadratic is going to be more complicated. You're going to have numbers or fractions inside the root and maybe a number outside the root. It doesn't matter. What matters is the sign in front of the radical. So if you have greater than 0, you're going in the positive direction, make your radical positive. If you have the less than 0, that means it's in the negative direction, then make sure the negative is in front of your radical because it's the downward direction. So it's not the up. Notice this is the positive direction. This is the negative direction. X is in the positive, means your y will be in the positive. If X is in the negative, y will be in the negative. So this is what's going to help you. It's very important. You will lose a point if you do not identify that. It is kind of a rare question, but it does happen. Means that you really need to pay attention to your domain statements and the direction of your inequalities. So again, understanding domain and range is more than just doing math. Domain and range especially is conceptual. It's understanding how the algebra and the graphs work together. So I hope this helps you. We've went through 4 applications. We've looked at the various type of domain statements that can be generated. I hope that you are starting to grasp and understand the meanings of domain and range, how you can arrive at them in these different applications. And I hope that this video has been helpful. I know it's kind of a lot to take in, but it's really the glue that kind of keeps all this function stuff together. It's not so much the procedures, but it's the concepts that relate all the procedures that you do. So hope you took notes. And again, thank you for joining me in the Zoom room.